Namaste to everyone. I welcome you all in my YouTube video channel. Today, I will deliver lecture on linear algebra, chapter Adjoint and Inverse of a Matrix. Lecture number 1, in which I will give the details concept about why the concept of matrix and determinant have come. Here we are dealing with linear algebra. But question is, why we add the term linear with algebra? That is, what is the meaning of linear? And that linear term is added with algebra. Linear means the linear has come from line. That is straight line. This is straight line. The equation of straight line is y equal to mx plus c. M be the gradient of the straight line, and here variables are x and y. In other form, ax plus by equal to c. This is the equation of the straight line. In this equation, we see that power of the variables x and y be 1. Power of x and power of y equal to 1. Here variables are x and y. A, B, C are constants. If we raise the power of the variables, for example, ax square plus by equal to c, then this will be the equation of a curved line, either this type, curved line. So this does not satisfy the term linear, means line, means straight line. Let we have two equations of the straight line. A11x plus A12y equal to C1. A21x plus A22y equal to C2. These are two equations of the straight line. These straight lines are drawn on xy plane. Here x and y are variables. So these two straight lines may either intersect or may not intersect. If they intersect, then we get a common point, value of xy. This xy, ordered pair xy, will be the common value of variables x and y for these two equations. And if they do not intersect, then they will be parallel in xy plane. If we consider the equations involving three variables x, y and z, let we have three equations such that each of equation involve single power of variables x, y and z. Also, each equation represents a plane. If we take two equations, first two equations together, then we get two planes and two planes intersect along a straight line. So if we work the two equations together, we get a straight line. Similarly, if we work second and third equation together, we get another straight line. If we take first and third equation together and work, then we get another straight line. Means we get three straight lines. These three straight lines may intersect at a single point or may not intersect, may parallel or may not be parallel. In linear algebra, we will get some terms and their properties which will indicate that these three straight lines will intersect at a common point or not. That is, unique value of x, y, z may be obtained or not, or they are parallel or not. Different conditions will be developed. Whatever we from these type of linear equations, we see that we have some coefficients of the variables. Here a11, a12, a21, a22. These are coefficients of the variables. These coefficients play important role for giving any structure, geometrical structure or anything. These coefficients are a11, a12, a21, a22. If we arrange these coefficients in two rows and two columns, here we have arranged this, and if we give the bracket this type, means here we have two rows. First row contains a11, a12. Second row contains a21, a22. First column contains a11, a21. Second column contains a12, a22. Then this type of arrangement will be termed as the mathematical term matrix. This is the matrix 2 by 2 matrix. Means we have two rows and two columns. Here columns. These are rows. First row, second row, first column, second column. Therefore, we define matrix as follows. A set of m multiplied by n numbers, that numbers are either real or complex, arranged in the form of rectangular array having m rows and n columns is called a matrix. Here we have m multiply n number of elements. They are either real or complex. This is the first row. First row contains a11, a12, a13, a1n, n number of elements. Similarly, second row contains n number of elements. Similarly, mth row contains n number of elements. Means we have m rows and n columns. These are row, first row, second row, mth row. This is first column, this is second column, this is third column, this is nth column. And this arrangement is known as matrix. This is denoted by capital A. We may also write this as Aij in short, m by n. Means this matrix is of size m by n. So we get that the concept of matrix has come from the linear equations. We arrange the coefficients of the variables of the linear equations in rectangular array. Means this is rectangular array that may be either square or rectangular. Now we will add different concepts on this arrangement, and then these concepts will help to improve a mathematics, that is linear algebra. Although you know the concept of multiplication of two matrices, but I would like to give a slight touch about this concept. Let A11, A12, A21, A22 and capital B equal to B11, B12, B21, B22. This is 2 by 2 matrix, and this is also 2 by 2 matrix. So for multiplication of these two matrices, A multiply B, we take here first row, here first column. First row A11, here B11 plus first row A12 multiply B21. This is called scalar multiplication. Next, first row, second column A11 B12 plus A12 B22. Next, we have not A13. So we start second row. Second row, first column A21 B11 plus A22 B21. Here, first row, second column A21 B12 plus A22 B22, and we get another matrix. This is also 2 by 2 matrix, means number of row B2 and number of column B2. In this way, we multiply two matrices. This type of multiply is called row multiply column. Firstly, first row, here first column. First row, second column. Here second row, first column. Then second row, second column. In short, let A equal to Aij, this is a matrix, M by N size, B equal to Bjk, this is N by P size. It is important to remember that for matrix multiplication, the number of columns here n of the first matrix will be equal to the number of rows of the second matrix. Then we may multiply these two matrices. Let ikth element of AB equal to Cik. Then Cik equal to sigma Aij Bjk value of j is n. Here also n. First suffix j, first is n. So j equal to 1 to n. And we get AB equal to a matrix whose elements are C, I, K. This is A by P size. This is the concept of matrix multiplication. Now, I will give you the concept of transpose of a matrix A. Let A be a matrix. This is the size 2 by 2. Then transpose of A is denoted by A prime, and this will be equal to, we arrange the elements of the row as column A11, A12. The second row will be changed into second column A21, A22. This is also 2 by 2. Now, I will give you the concept of determinant of a 2 by 2 matrix. Let A be a 2 by 2 matrix. This is 2 by 2. Determinant of A is denoted by this type. And this is equal to, we multiply this diagonal A11, A22 minus A12 multiply A21. Since the elements of A are real or complex, here we have calculated this. Here multiplication, here subtraction. So this is the multiplication subtraction of real or complex number. So this value will be real or complex. So determinant of a matrix is a real or complex valued function. Now I will give you the concept of cofactors of a matrix. Let A be a matrix. It is 3 by 3 matrix. Then cofactor of A11 we find. Firstly, we see that here 1 1. So we write here minus 1 to the power 1 plus 1. Then we cancel this column and this row. Remains A22, A23, here A32, A33, and we find the determinant. And this value is the cofactor of A11. Now, cofactor of A12, this is 1, 2. So, we write here minus 1 to the power 1 plus 2. Here 1 2, this contains in the first row and second column. We cancel first row and second column. Remains A21, A23, A31, A33. Determinant. Now cofactor of A13. A13 contains in the first row and third column. We cancel first row and third column. And here we write minus 1 to the power 1 plus 3. Cancelling first row and third column. Here remains A21, A22, A31, A32. Let name of this cofactor of small a11 is capital A11, and this is capital A12, this is capital A13. Now cofactor of A21 is in the second row and first column. We cancel second row and first column, remains A12, A13, A32, A33, and here minus 1 to the power 2 plus 1. Now cofactor of A22, this contains second row and second column. We cancel second row and second column, remains A11, A13, A31, A33, minus 1 to the power 2 plus 2, A11, A13, A31, A33. Determinant. This cofactor of A23 is minus 1 to the power 2 plus 3. Here A23 is in second row and third column. We cancel this and this. Remains A11, A12, A31, A32. A11, A12, A31, A32. This is minus 1 to the power 3 plus 1, 31. This is in the third row and first column. We cancel this and this. Remains A12, A13, A22, A23. Here cofactor of A32, minus 1 to the power 3 plus 2. This is third row and second column. Remains A11, A21, A11, A23. This is minus 1 to the power 3 plus 3. This third row and third column cancel. A11, A12, A21, A22, and name of these are capital A21, this is capital A22, this is capital A23, this is capital A31, this is capital A32, this is capital A33. These are cofactors of each element of the matrix A. Now we find the value of the determinant of any matrix. Let we have a 3 by 3 matrix. This is capital A. Let B by another 3 by 3 matrix which contains the cofactors of corresponding elements of matrix A. Capital A11 be the cofactor of small a11, capital A12 be the cofactor of small a12, and similarly we get other cofactors. Let determinant of the matrix A is denoted by these two vertical lines, this and this. One left side of A, one right side of A. This denote the determinant of the matrix A. Now we take these values A11, small a11, capital A11 plus small a12, capital A12 plus small a13, capital A13. This means the scalar multiplication of the first row of matrix A and first row of matrix B means we multiply the element with corresponding cofactor plus this element, second element with corresponding cofactor, next third element of the first row with corresponding cofactor. And similarly, if we take the elements of the second row and we get the scalar multiplication of the elements of second row of matrix B, that is elements of second row of A with corresponding cofactors, and we add. Similarly, if we take elements of third row of matrix A and multiply with the corresponding cofactors, this third row of matrix B, and add them. Similarly, if we take the elements of first column and we multiply with the elements of first column of B and then add, that means we take elements corresponding cofactor multiplication, element corresponding cofactor multiplication, element corresponding cofactor multiplication, and add them. And in this way we will get that if we multiply the elements of any row with corresponding cofactors and then add, we get the value of the determinant. Otherwise, if we take the elements of the first row and cofactors of the elements of the second row, this second row, and we multiply then add, we will get value 0. Small a11 multiply capital A21 means cofactor of this, element this, cofactor this, and the value will be 0. So if we take elements of any row and then scalar multiply with cofactors of other rows, then we get value 0. By a particular example, we may describe it. Let A be a matrix. This is 2 by 2 matrix. Here in the first row we have numbers 1, 2. In the second row 3, 4. We may write this as A11, A12, A21, A22. This is 2 by 2 matrix. Determinant of this matrix is 1 multiply 4 minus 2 multiply 3 equal to 4 minus 6 equal to minus 2. Here cofactor of 1 means A11 is minus 1 power 1 plus 1, and we cancel this column and this row, remains 4. Similarly, we may find cofactor of 2, that is cofactor of A12. Here minus 1 to the power 1 plus 2, we cancel this column and this row, remains 3. So this is minus 3. And in this way we may get other cofactors. Now A11, its cofactor capital A11 plus A12 multiply its cofactor capital A12 means we take the element of the first row with scalar product of its cofactor. So this is A11 is 1 multiply capital A11 is 4 plus small a12 is 2 multiply capital A12 is minus 3 and this is minus 2. This is equal to the determinant of the matrix. Similarly, this is the element of the second row and scalar multiplication with its corresponding cofactor. This is also minus 2. This is the value of the determinant. Now we take elements of first row A11 and A12 and we take scalar product with the cofactor of the second row A21 here A22 capital and we see that value of this is 0. Similarly, we take elements of the second row and we multiply scalar multiplication with the cofactors of the first row capital A11 capital A12 and we get the result 0. So in this way our verification is completed. In the next day I will give you the concept of adjoint and as far as possible the properties of disjoint. Thanks for watching my video. If you are satisfied with my presentation and contents, then please click on like button. And if you have not yet subscribed my YouTube channel, then please subscribe my YouTube channel. Thank you.